Hello, in this video, we're going to go over the stack pointer in MIPS assembly programming. First of all, though, some general knowledge before we get into some programs. Stacks in general follow the last in, first out principle. So a good example of this is a pile of plates, right? You don't take, if you're going to scrub a plate, you do not take the one from the bottom first, you're going to take one from the top. And stacks are used in all sorts of programming situations, and this is no different. So the stack pointer, which is SP register, it grows downward in memory. So before calling a function, you push or store the registers into the stack. And then after returning, we pop the registers. In principle, there's some variations with this depending on how you're using the stack pointer, and we're going to see 4 examples here. And regarding saving and restoring registers, the caller save registers must be saved by the caller if needed, because it shouldn't be the callee's responsibility to do that. The callee save registers are saved by the function itself. Again, we'll see an example of that in these programs. So our first application with the stack pointer is going to be when we are working with a recursive function. So the most commonly thought of recursive function is factorial, right? So that's what this program is going to do. So we stored 5, for example, which is going to be our argument. Again, remember, when we're labeling functions here, we're going to refer to as the name, give a short description, inputs, and outputs. So in this case, Factorial only has one input, which is n, whatever n is. In this case, we're using register A0. So we're going to store 5 into that and jump in link and call it. So how this function works is we make immediate use of the stack pointer. So again, as you'll see a couple examples, this will start to make sense. What this line does, line 33, is essentially we're making space on the stack because we're subtracting, because remember, the stack grows downward in memory. So, and then we save the return address onto the stack because we're gonna, as you see down here, you see another jump and link instruction, because in that case that's going to overwrite the return address. So we need to make sure we're actually saving that. And then we're saving n, which is our input, into the second entry on the stack. So again, as in all recursive functions, there's a base case, right? So our base case here is if n is less than or equal to 1, we just return 1. Okay? So simply put, we if that's the case, we're done, right? And then we can move on to returning. Otherwise, we need to decrement, and we need to decrement A0, and we need to call Factorial again. So jump in link the Factorial again. So go back and keep doing it until we go all the way down to our final thing, right? As you can see here, once we're done, we are restoring our return address, right? And as you can see here, we're restoring our original n. So that's what these stack pointers are for. Because the most important thing with recursive functions is that our return address is not being overridden by something else. Because if that would be the case, the program would just not work as intended. So simply put, we return to the caller. We move it because we need V0 as our argument for the syscall. And then we perform the syscall, we print the result, and then we exit the program. So let's take a look at let's take a look at the output. That's assemble and run it. As you can see here, this checks out. 5 factorial is 120. We could also try, let's try 4. Assemble, run, 24. So this program checks out. So next, let's move on to another situation in which, in case we are passing too many arguments into a function. So as you can see here on the right, our list of registers, there is only 4 argument registers: argument 1, argument 2, argument 3, and argument 4. In this case, though, we want a function that comes up with a sum of 5. So why I purposely left this description blank is because we're going to do it together. So this function calculates the sum of 5 numbers. Our input, our first set of inputs is A0 through 3, which is the first 4 numbers. And then our next input is from our stack, which is our 5th number. You'll see that in a second. So let's get started here. For simplicity's sake, because we don't really need to care about user entering things in again. So we just load immediate A1, A2, A3, A0, A1, A2, and A3. And then we're pushing our 5th parameter into the stack. So before we even call jump and link to sum 5, we need to already make space on the stack for that 5th parameter, right? So in this case, we only need room for one entry into the stack. So that's why we're subtracting by 4. And then we're storing our 5th number that's loaded into temporary register T0 into the stack. And now we can call the function. So scrolling down here, we are making more space on the stack because we need to save our return address, which because that's very, again, you need to do that every time in these functions. So now we're going to use temporary register T0, loading the 5th parameter from the stack. So that 5th number is going to go into there, and we're going to add the numbers. So first we're adding A0 and A1, then that collective sum, and we're going to add A2, then we're going to add A3 to that, and then we're going to add T0, which is our 5th number from the stack. So now we can restore our return address, deallocate the stack space, and return the caller. Again, I can't emphasize enough. Constantly making sure you're allocating and cleaning up your memory is very important in assembly, because this isn't something like Java or C where that's not really a big deal. In assembly, it is, because there's only so many registers that you have to work with. But you can use your stack pointer essentially for the all intents and purposes as much as you want. So moving back, again, making sure our V0 is not overridden, printing the result, cleaning up our stack, and then exiting the program. So let's take a look. That's assemble and run it. As you can see here, this checks out because 10 plus 20 plus 30 plus 40 plus 50 is equal to 150. All right, so now let's move on to our next example. So the concept of the stack pointer is implemented in this program in terms of local variables, because as you can see here in the main, we're not interacting with the stack at all, but we are in the compute expression function here. So the point of this is obviously this is a simple program, but maybe think of if this was a really complicated program and there was tons of calculations going on, tons of instructions. Again, there's only so many registers here, but you can use your stack pointer as much as you want. So that's what we're going to do. But that's getting our main. Let's start with our main real quick though. As you can see here, we're just simply loading in the function parameters. We're using up our number of arguments, not argument registers, but we're not going over that because that's not what this program's about. We're jumping and linking to compute expression, and then going down here, function compute expression. Simply put, this computes this expression using local stack variables. So our inputs are the numbers for the expression, and then our output is the result. So as you can see here, immediately we're making space for our two local variables, which is going to be a plus b and c minus d, plus our return address. We always want to make sure we are keeping track of our return address. So that's the first thing we're going to store, even before all these calculations. That's always good practice because you're going to probably get to the point where you are coming up with functions that have some sub-functions, and maybe those sub-functions have their own sub-functions. So it's very important that you are making sure you save your return address right at the start. So the first thing we're going to do is we're going to compute our first local variable here, which is a plus b, and we're going to store that into the stack. Assume that between these two things, there's maybe a few or a bunch of other hypothetical calculations that could overwrite registers, so that's why we're using our stack. And then we're computing the difference, so our second local variable. So difference equals c minus d, and we're storing that difference into the stack. Assume that there's many hypothetical calculations later, and now we can get to coming up with our result. So in this case, we're going to load our sum from the stack, and we're going to load our difference from the stack, and that's how we're going to get our result. But before we return, we have to make sure that we are cleaning things up. So we restore our return address, and we deallocate the stack. So we're 100% doing cleanup here. Making sure you clean up is very good programming practice in something like Java and C, but it is especially important here because, as I said before, you only have so much room. And then we return to the caller. We're making sure that V0 is not overridden. We print the result, and we exit. So let's test this out. As you can see here, this is the correct answer. Okay, let's move to our final program here. So the point of this program is going to be to explain how to store multiple, because again, we have only two variables for return, v0 and v1. But this program needs to return the sum, product, and the difference. So that's 3. So our inputs, real simple, is a 0 through 1. That's going to be our numbers. And then our outputs are going to be V0 through 1, and that's going to be the sum and product. But there's also the stack, which is going to store a difference. And obviously you can expand this as much as you want, but 3 examples are enough for this program. So let's get started here. For this one, I decided to have some data here that make it clear because we have multiple outputs. But our 2 parameters are 10 and 4 for A and B. First, we need to allocate the space for the third return value on the stack because you can't do that in here. You have to do that in the main. So we're allocating that space. We're passing the pointer to the stack. We're calling the function. So going down here, we're doing our simple add and multiply. And then we're coming up with our difference, which we're going to store onto the stack. And then at that point, we can, because we can't do the cleanup yet because we have stuff in the stack. So we need to return. And then we're going to move our sum, product, and difference into our temporary registers. And then we're going to print out our sum, our product, and our difference, which again, the difference is loaded from the stack. Now we can clean up, and then we can exit the program. We always clean up the stack pointer before exiting the program. That is good practice. So with 10 and 4, let's take a look. Let's assemble and run. And this checks out. Our sum's 14, our product is 40, and our difference is 6. So I hope this video was a good overview of the stack pointer. Again, once you figure this out, how that works and what's the best practice, I would say you've graduated to becoming an intermediate programmer in assembly, because this is a key gateway into understanding this overall topic of assembly language. So feel free to leave a comment if you have any questions. I thank you for your time, and thank you for watching. Have a good day.